Okay, to round off this section, so what we did last time, we proved this theorem, the construction of a manifold structure on the coset space. And what was explained is that this turns the coset space into something we will now now on call a homogeneous space. So this is the following definition. Well, if we have a Lie group, uh, so for G a Lie group, and H a closed subgroup, the manifold we just constructed in the last theorem, G mod H, is called a homogeneous space. Those are homogeneous spaces. Okay, which explains the title here. And recall, so we have a lot of information about this, namely in the last proof, one of the essential things which also underlies the idea of a homogeneous space is that we basically can get a proxy of the multiplication. So we have this commutative diagram. Upstairs we have the multiplication of the Lie group, and downstairs we have the canonical action on the homogeneous space, which is smooth. And here we have the quotient map, and this action we call sigma, which is just left multiplication of group elements on the cosets. So we have this commutative diagram of smooth maps, which somehow allows us to use the multiplication as something which acts on this homogeneous space. And the way in which we constructed the manifold atlas, let's just recall the proof detail from the proof of the thing. So what we did, we built this map psi, which turned out to be a homeomorphism. So we have the psi here, um, and so this was a homeomorphism, and this gave us a chart around the coset generated by the unit, right? And then all the other charts were basically constructed by translating this chart to a chart we called psi g. This is downstairs here, and this is in essence it's just the chart, and we left translated this to a neighborhood of the coset we want to be working as, and we use the group multiplication, or in well, on the homogeneous space we used the canonical action for this. And this has a nice consequence if you're just studying how these charts are constructed, and what this commutative diagram we have here, what this brings to the table. So if we think about what this means, we get a lot of information of the construction both of the charts and the fact that the charts were constructed, or this initial chart psi was constructed with respect to this map PE we constructed there. And this map PE exploited that we have a diffeomorphism between the exponential of this map V of this set VE times H, and the Cartesian product of VE with the H. So this was integral in the construction, and this allows us to get the following corollary from the construction. So this is a corollary we get now for every homogeneous space. And the proof is basically by studying how the charts are built, and we leave this as an exercise. So let G be a Lie group, H a closed subgroup, and we are considering the homogeneous space given by this construction. Then the corollary from the proof of 426 is for every point in the homogeneous space, there exists a smooth map sigma. Sigma is defined on an open subset of the homogeneous space. It goes to G such that if I compose sigma with the quotient map, the canonical one, I get the identity on the open set U. So we also say sigma is a section of Q, and the chosen set X is inside of the set U. And in addition, we have one nice property. We can build with this section a map M sigma, which is defined on U times H. And what it does, it goes to the product of sigma of U times H and sends a U and an H to the product of, first we apply the section to U and then we multiply with H. This is a diffeomorphism onto an open subset of G. So in a way, we can describe an open neighborhood of a pre-image of our point X in the group G as one of these product neighborhoods where we take the section and pull the open neighborhood of X with the section up into the group G. And then we multiply with the whole subgroup H we have quotiented out. And the proof of this is not hard, but it's maybe a nice exercise to study how this follows directly from the construction in 426.